Yep.
And you can see my slide prezo.
Yeah, I can see that now.
Thanks, Tony. You scared the crap out of me. I'm going to have to go through a bunch of relays away that I have in a drawer, I think. And my house has actually been hit by lightning twice. Second time blew up everything that plugged in the wall. So I have a lot of respect for current. But I'm not talking about that today. What I'm going to talk about shouldn't kill you anyway. I'm going to talk to you about Swift on microcontrollers, and specifically DSL, which is something I've been working on for the last few months. I'm going to run through a few slides to give you guys a little background, and then hopefully run a couple live demos, and then we can do some Q&A. So I'm a partner in a mobile software company. That's my day job. And I spend a lot of time writing code for iOS mostly. And I use Swift. So microcontrollers has been my hobby for quite a while. And it's really hard for me to write in C and C++ anymore. Kind of been spoiled after using things like Swift. So I was pretty excited when Swift for Arduino, when I found it. It's a commercial product you may be familiar with. I think Carl, the author of it, is on the call here. It's an awesome IDE, and it's got a compiler that lets you write in Swift and compile your code and send it right down to an Arduino. And he's got a roadmap where he's looking at other microcontrollers as well. And if anyone's interested, we can maybe chat a bit in the Q&A, or you can talk to Carl kind of offline. So a few months back, I started toying around with the idea of a new Arduino framework, something that's more modern and declarative, just basically easier to use for a lot of the common stuff that I find myself doing in the embedded world. Things like reading sensors, detecting push buttons, lighting LEDs, playing music, tones, that kind of thing. And I call this EDSL since it's intended to add a domain-specific syntax to small embedded systems, specifically microcontrollers. So what I'm going to talk to you about today is still a work in progress. It's by no means complete, but one of my goals is to start getting some feedback from folks. So what led me down this road? Well, when it comes to the Arduino, I've been using it, I think, since around 2008, maybe. I'm not really sure. I like the low cost. I like the capabilities for that money. That you can get the boards just about anywhere. They're getting cheaper all the time. There's a lot of shields. There's a lot of add-ons, things you can plug in. And I actually like that there's no operating system. So I can be in total control. And for a lot of the things that I do, an operating system is really overkill. And if I do need one, then there's plenty of options like the Pis and whatnot to do that. Now this leads to some issues. However, what I don't love so much about the environment, the IDE, I don't know how many guys use it. It's written in Java. It's kind of clunky. It's old. And like I said, I don't like writing in C anymore. I've written my share of that, and I'm kind of been there, done that. Thanks to what Carl's done with Swift for Arduino, I don't have to use that IDE. I can write in Swift. So really those two, they were my biggest pain points. Those two problems are pretty much behind me. And there are a lot of libraries available for Arduino, as you know. They're written by a lot of different people. Some are great, some not so much. They tend to focus, however, on the shields or the plug-in boards. So you might want to plug in Bluetooth or Wi-Fi or a stepper motor driver or something like that. And then you can go get a library to support that. What I haven't really found, and I certainly haven't found good, is a way to manage kind of these everyday tasks I mentioned earlier, these common peripherals. As you know, the microcontrollers are very, very constrained. Most of the time I use an Uno. That's got a whopping 32K of program space and 2K of RAM. So any code that is going to manage these tasks has to be pretty efficient. And then you get to the API, the basic Arduino wiring API that we use today. It was designed for C, and it dates back almost 20 years. And I think it's great. It's made microcontroller programming accessible to millions, but it doesn't really take advantage of things that modern languages like Swift can offer. So these last three areas are things that I've been thinking about and thinking they could be improved. And that's kind of where the idea of this EDSL came from. So here's an illustration. I don't know if you've used Swift for Arduino, but this is kind of how it works. At the bottom, there's the hardware layer. The ATmega is what powers most of the Arduinos. On top of that, there is an AVR library that provides Swift standard library, wiring, some custom APIs. And you can also, as I mentioned, these libraries, you can bring in other libraries to provide access to other things. And then at the top is where we write our programs, the user programs. And this does all work, but it forces us to use legacy APIs, limits our ability to adopt Swift style. And it makes it really nearly impossible to move one program I might write on an Arduino over to another platform. And the other problem I run into all the time is when I want to work with multiple peripherals simultaneously, read a bunch of buttons at the same time as reading a bunch of sensors, debouncing those switches and smoothing my sensors, flashing LEDs, all at the same time, which is really not the purpose of my program. It's just kind of the UI. This becomes really complicated, and I spend a lot of time on it. It just doesn't seem right. So here's an alternative approach that I've been looking at. At the bottom, again, sits our hardware, but here we can look at maybe targeting other MCUs. And then sitting on top of that is a really thin hardware abstraction layer. And this gives the layers above it a consistent platform neutral API. So it's the bare bones stuff that you'd need for, setting pin modes and reading and writing digital signals or analog signals. And this layer would be highly optimized for each platform that it's built for. And then the user programs can now obviously access the hardware abstraction layer, and that could be then in theory moved to other platforms. Now, hardware abstraction layer is great, but it's also, as I mentioned, low level. So when you start to get into a program that does anything useful, it's a lot of boilerplate code. This is kind of where the EDSL comes in. It's really designed to provide a model to get at some of these common needs. It is a declarative syntax versus imperative. I'm not sure how much you guys have talked about that, but it really is something that I'm finding fascinating, especially in the embedded world, where you can express your business logic without really describing the flow. The flow is kind of the recipe, like, okay, make this pin mode an input and then write it to high and then do this and do that. And you're describing a very detailed series of instructions when all you really want to do is turn an LED on. So declarative, you kind of declare what I want to do, not necessarily how I want to do it. So that was one of the kind of tenets behind EDSL. So kind of in a recap, it's really meant to be modern and portable, and then provide a lot of power, but also event driven. This is an interesting point because, as I mentioned earlier, you don't have an operating system. If you're using Linux or iOS or Windows, you have an event driven system. Well, you don't have that in the bare bones Arduino, so EDSL provides that, and that's kind of one of the keys to simplifying a lot of these things I'm talking about. So here's a really simple example. If you've ever done any programming on an Arduino, you've seen this program, the Hello World of hardware. Basically, you set up a pin to be an output, and then you sit in a loop, and you write the pin high, and you delay, and then you write the pin low, and you delay. Nothing wrong with that. It's pretty straightforward. I've taught young children how to do this. Let's look at the equivalent over on the DSL side. You don't really see a lot of difference here, but there are a few keys. And the EDSL side, you're going to declare an LED, not necessarily a pin. And you're going to use a command to set the blink times, and then you're going to tell the LED to blink. And then the boilerplate for an EDSL program, it's based on an event loop, as I mentioned. So here we have a board update loop where you basically call any component that you want to be updating. And that's the entire program. Now, granted, it's a little bit shorter, but it's not substantially different. But the key, and you'll see in a minute why that matters, is there's no delays here. So I'm not hard coding delays. And as you know, when I'm sitting on the left-hand side in a delay, the Arduino is doing nothing. Can't be running any of my user program. So if we look at this in a little more complicated example, let's say we want to blink 2 LEDs. You think that'd be pretty easy. Now what I've done here is I highlighted in whatever that is, salmon, I guess, the code changes. So what I had to do was, use another pin, but now I can't use delays because I want 2 LEDs blinking at different rates. So I have to go to a more sophisticated program, which now is keeping track of, how long an LED's been on, and it's a time to turn it off, and do that in a loop. That's not terrible, but I think you can see it's not anywhere near as readable as the previous example. Now what DSL does is if you bring that in, here's what the same program running on EDSL would look like. All we really had to do was copy the 3 lines that declared the LED, set the blink times, and told it to blink. And then we just supplied different values for the blink times. And then we add that new LED, the update loop. And this is a much simpler, especially if you try to go to 3 or 4 or 5 LEDs. Now, where it really gets interesting is you think, well, what about adding fading? I didn't bother to put the code here because it wouldn't fit in the classic way. Now, fading, what I mean by that is when the LED is turning on, it's ramping up, and when it's turning off, it's fading down. What's nice about the EDSL is, again, code changes are highlighted here. All I had to do was add 1 line of code for each of the LEDs, indicating, when I turn an LED on, I want it to ramp up, in this case, in a 1/4 second. And when I turn it off, I want it to ramp down in a 1/4 second, and then different for the second LED. Now, one thing to note here is you'll notice throughout, and we'll talk a little bit more about it, is I'm expressing things in seconds here with floats. And this is an interesting thing because while I mentioned it's a microcontroller, has to be efficient, there are ways to use floats for your user-facing API and still be efficient behind the scenes. And that's what we're doing here. And primarily because as you move from platform to platform, it's sometimes hard. A good example is when you're doing A to D conversion, you read a value in Arduino. If it's, a typical Arduino, it's 10 bits. So you have a 0 to 1023 reading. If you add an external A to D, which I've done, maybe that's 12 or 14 bits. And then you've got all these conversions you're doing. So in the DSL world, everything is expressed in 0 meaning nothing, 1 meaning everything. So a sensor comes back 0 to 1, no matter how many bits. Times are expressed in seconds, which is fairly natural for humans. Anyway, so that's a quick overview. Here's the components that I've been working on. It's quite a long list. I sat down and thought about the things I typically hook up and made a list. The last item is other. There's going to be more. I've only been kind of doing this in my spare time the last few months. I've got just about everything I think everything on the left-hand side is implemented and working to some degree, if not fully. And the stuff on the right is kind of coming up as I work through it. So what I'm gonna do here is hopefully switch over and give you guys a little bit of a demo here. Give me a second. All right. Are you guys seeing, it's probably not yet, huh? There we go. Can you see my board?
No, we're just seeing
so this is
demo in black and white background.
Okay, it's probably, that's probably my other camera. Let me stop sharing. I am going to come back to that because I do want to show you some code. In my conversation window, I'm not sure if you guys can get to that. Where my face would normally be if you were looking at me. Do you see the board there?
Yeah.
Okay. It isn't terribly important to see it. It just kind of show you it's live. So this is an Uno clone, basically. It's one from SparkFun I'll be using today. In addition, this is a small board that I kind of designed and built to help me out with this project. You saw the list here of all the components. Well, I needed an easy way to test out the code without having to be chasing down bugs because I knocked a wire off or hooked something up wrong. So I kind of came up with this. It's an I/O board. It's a shield, basically. It turns out to be kind of cool and handy. It's got a couple 7-segment displays, some shift registers, 3 pods,
Mark,
3 buttons.
If you stop sharing your screen, people will be able to see it.
Yeah, I'm not sure. Could you see it now? You should have been able to see both, but at any rate,
Yeah.
Okay. How's that?
Yeah, that's fine.
Yeah.
Okay. And then it's got a speaker, some iLEDs, some RGB LEDs, excuse me, and some regular LEDs, temperature sensor, light sensor, and then I ran out of space because I was trying to make it fit in the shield format. Anyway, that's what we'll be using today. Let me just plug this in quick. right, so here's the first program. And again, it's just the, traditional, and again, it's just the traditional, just a second here, I'm doing a little too many windows here. Typical Blink program. And I'm in Swift for Arduino. So this is the program I kind of showed you. It's the hello world. It's basically 2 lines of code. You declare an LED, tell it what pin it's on, and you tell it to blink. And that's for the most part it. And it's not, I won't switch my screen for now, but it actually will compile and run. It's not that exciting. It blinks an LED. For those of you that want to look at the small window, you can see it. But again, this isn't terribly interesting because it's a pretty simple program. If we switch to 2 LEDs, let me share the second one here. This is the one we were talking about where it gets a little complicated in the traditional Arduino world. Here, it's not so bad. You have a couple of LEDs declared. You set the blink times. You set the fade times. You actually execute the blink command. And that's it. And I will send that one up. And hopefully you'll see this. And what's interesting here is we've got, 2 LEDs, ignore the LED, 2 LEDs going here, different rates, and they actually are fading. I don't know if you can tell with the camera or not, but they're actually fading in and out as they go. Let's move on to something a little more interesting. Okay, now we have a little different program here. I'm going to use all 3 LEDs that are on my board. I've got 3 red, yellow, and green. And I've also got 3 buttons, as I mentioned. So and again, the declarative style, I'm simply declaring, I've got these LEDs and here's the pin they're on, here's the buttons, here's the pin they're on. And then in the case of DSL on buttons, you get a callback whenever the value of that button changes. So there's a callback method called onValueChanged, and it passes in, it provides you the state of the button at the time. So it becomes very easy in this case to say when button 1 is pressed, set the LED state to the button state, on or off. And then we simply replicate that for 3 buttons. And again, there's a board update loop. And now when I pause sharing, does that actually give you guys a bigger image of the board, or I'm not sure if that's doing what I think it's doing. No? Yes? Maybe? All right, here it's running, and real simple. I got my big fat finger on here. I push 1 button, it lights, push the 2nd button, it lights, push the 3rd button, it's lights. Now what's of note here is these buttons are actually all being debounced as well. And if I felt like it, I could provide the level of debouncing to balance responsiveness. If you got a really noisy switch, sometimes that matters. So there's a real simple level of debouncing added to these. All right, I will move on to RGB LEDs, which I don't know how many guys work with these. They're one of my favorites. I do like messing with them. They're a little tricky to program. And this is where DSL has really helped take a lot of the pain out. In this case, what I'm going to do in this simple program is I've got a potentiometer that I'm going to use, and I've got an RGB LED. It's a ring, actually. There's 12 of them in a circle. And this is what how the declaration for an LED, RGB LED looks like. You tell it what pin and how many you have. And then in this case, all I'm going to do initially is simply turn them on. Part of DSL is it provides some basic color support, so you don't have to worry. If you want, you can go create custom colors using HSB or RGB, but there are a handful of predefined colors for you. And you can see the result here. Now I have these, hopefully, yeah, it's blowing out the camera a little bit, but there they're all on in blue. And what I'm going to do here is simply bring in some additional code to show you a couple other functions. There's one called rainbow. I bet you can probably guess what that does. As I mentioned, there's some predefined colors. It's actually 12 steps around the RGB color wheel. So when you say rainbow, you get a nice smooth gradation between colors. This is a little bit tough to see on the screen, but you've got a rainbow effect there. And this is really nice when you get a large strip. Like if you have a strip of 50 or 100, you get really smooth, beautiful gradations between the colors. And again, with a pretty simple one line of code. Another one I was playing around with is called color gradients. And rainbow is actually a color gradient. It's just a color gradient from the beginning of the color spectrum to the end. In this case, what I'm going to do is I'm going to create a color gradient. I'm going to tell it I want the first color to be blue, and I want the last color to be rose. So it's a slight variation of the previous one. And as soon as this program uploads, you can see there, this is basically blue through the ambers and violets. I'm sorry, through the violets to pink. I'm not going to show you random standard colors. It basically just takes the 12 standard colors and randomizes them. Where that's interesting is where you start to get again into a large strip. And here's one that is a brightness gradient, and it allows you to specify a color and what brightness you want the first element to be and what brightness you want the last. Now I'm using very small values here, so hopefully they will show up on the camera here because they tend to blow out. Probably hard to tell, but they're actually various brightnesses. Hard to tell through the camera because it's all too bright for my camera. Switch here to a different one here. Now this is going to start just like the last one ended. It's actually, you can see here a brightness gradient command. Again, blue starting at this level, going to this level, but this time I'm specifying a count of 9. And what this shows is one of the modern features of modern languages is you can specify optional parameters. So there is a parameter for count, and if you don't supply it, it uses the entire, whatever you've defined as the entire LED strip or ring. So in this case, I'm telling it, no, I only want to use 9 of them. And what that'll do then is allow me to leave out 3 of them. And where that becomes interesting is then if I go to the next level and introduce some animation, which is something that can be really difficult to do with strips. Here you can see the code is quite straightforward. You just say animate, and you've got to give it some information about what kind of animation you want. I want a rotation. I want it to move to the left, which I think is anti-clockwise. I'm not sure on a ring. And then I can specify a frame time, which is how long each step is held. In this case, we'll do 20 frames per second animation. And it's one of the reasons I left 3 of those off, so you can actually kind of tell what's happening. It's still compiling here. There we go. And now we've got a really nice animation. And again, whether it's 9, 12, 50, or 5,000, no matter what's on your, it could be rainbows or whatever, you get a simple command to animate them. And I think I'll do one more, and then I'll let you guys ask me some questions here. Let me just get the last one up. This one here is very similar, except what it shows here is, you saw the on command earlier. We can tell LEDs to turn on. And again, there's some optional parameters, which I had left out earlier. Here, I'm able to say, I want it to be blue, but I want you to start at pixel 0 and light up 4. And then I want you to use red, start at pixel 6 and light up 4. And then I want to animate them like we did the last time. And So it gives you a fine degree of control. So you can do all sorts of interesting effects. And I said one more. Now there's truly one more, I promise. Let me just get to my desktop real quick. I got to pull up one other thing. I'll be right there. Okay. I'm gonna start the Q&A. I bring the next one up. I got a few too many windows up and I'm losing track. So feel free to fire away. I got a couple closing comments, but I'd like to kind of get some feedback from you guys in terms of the what I've showed you so far.
Yeah, I just had a question about what's actually happening behind the scenes. So you're obviously writing the code in your DSL, but what happens after that? How do you actually get the code onto the board?
Sure, I'm using Carl's Swift for Arduino IDE, which all my code, as you saw, it was all written in Swift. So I'm using his off-the-shelf product, which you can get off the App Store today. And then I wrote actually the DSL quote-unquote library is all written in Swift. It's just all pure Swift code. So the idea there being, if I go to any environment that runs Swift, DSL should be able to be compiled and run there. It has to have a very thin layer to talk to the hardware. That's the hardware abstraction layer. What I'm using right now is literally digital read, digital write, analog read, analog write, and ticks. That's it. So as long as I could get equivalent functions from any hardware platform, everything you're seeing here should work fine. But I am using Swift for Arduino right now, and that provides compile and upload, very similar to the Arduino classic environment itself. Are you guys actually seeing my board now? I'm not sure if
I can see your board yet.
So this is kind of the mega demo. This has kind of got, just to kind of show the robustness, I've got 3 LEDs. They're blinking at different rates. I've got a 7-segment display that's driven by a pot here. I've got an LED strip that I can brighten and dim with the other pot, and I can change the hue with another pot. And again, it's all running simultaneous using commands, pretty much like what you just saw. So there's no complex code. I kind of acid tested this with one of my grandkids, brought my 11-year-old over who doesn't even write software. And, within a few minutes, he was running LED strips and blinking LEDs without me really giving him much more than 5 or 10 minutes, showing him a couple examples like I did you guys. So the goal really wasn't to make it for kids. It just happens to work out well. The goal for me was, I want to go write my next cool Arduino project. I don't want to spend lots of time trying to figure out how to make, the peripherals work. And I wanted to write things, and like I say, in a more modern way.
Very cool. Any other questions?
Yeah, how big is the size of the code compared to writing it in normal processing and wiring or whatever it's called?
It's a good question. There's a couple answers to that. Right now, I'd say it's very comparable. There's some, it really depends on what you do. The goal is to make it smaller, and I think it will be. For example, HAL was something that Carl was starting separately from me doing this. And what it aimed to do was to eliminate wiring, because wiring is fairly fat. It's pretty big. As soon as you start to do anything useful, your program is a balloon. So, I compiled a HAL version of some of these demos, and it knocked off, this is early, but it knocked 4K off. of the programs. And again, with a 32K environment, chopping off 4K is huge. This program you see running here with everything and not optimized, because what I did, my goal, and this is kind of how I usually work, is I wrote it to work, in other words, to function. And now I'm working with Carl to go back and understand, when I write my Swift this way, what is actually happening under the hood to generate the code. In some cases, you know, if I have a function call a function, the code could be twice as big as if I just made a larger single function, right? And we passed a parameter to it. The way code is compiled for a microcontroller is really not obvious all the time. Well, it's probably true for any system. But I do believe that I'm very confident, because some of these components I wrote are just 50 to 150 lines of code. There's not a lot there. They were meant to be pretty tight, but there's going to be some further optimizations. But the goal is really to have an equivalent program be smaller, and I think we'll get there.
Cool. Thank you.
Any other questions, anyone?
I was wondering about the DSL. Is it inspired by SwiftUI, or is it just your own?
Yeah, it actually kind of is. I was starting to learn SwiftUI, and I said to myself, this sure is nice, and I wish I could do it on my microcontroller. And I remember that was my kind of the initial thought. There are some differences, obviously, and there's some things I'm going to do. Like you'll notice in some of the code, there's LED dot blink, and what I'd like to do is dot chaining, so I can just say dot blink, dot on, dot brightness, and even make it more terse. Swift for Arduino currently does not support classes, mainly because of the overhead, memory management, and lots of things Carl could talk about. So everything you see is done with structs, which are, it eliminates. I can't return a writable struct from a function, so I can't do dot syntax chaining yet. I think that'll be coming, but that would be one thing I'd like to see happen to make it even more like SwiftUI, is to eliminate repeating the object or component name in every single line of code.
Right.
Okay, thanks. Thanks very much, Mark. That was pretty good.
You bet.
Very nice to see a little bit of a microcontroller code. Looks very useful.